But let's start. So we're on part 5, and mechanics, part 5. So last time we talked about, this was 2 weeks ago actually. Last time we talked about constrained systems and generalized coordinates, right? Constrained systems. And we talked about generalized coordinates again. So if you haven't been around for one of these in the past, I put all of the notes on Discord, so !Discord, and you can find the notes under the discussion note series. So you don't have to actually write anything down. You can actually just follow along if you'd like to do that. So there's that. Okay. And so we did constrained systems and generalized coordinates. We did degrees of freedom. So we did constrained system. We did degrees of freedom. Talked about what some of degrees of freedom looks like, both in classical mechanics and quantum mechanics and mechanics in general, as well as we talked a little bit about some chaos theory, about how degrees of freedom can matter when it comes to how in conservation, how laws, how degrees of freedom affects chaos, right? And then we ended with a proof that basically said with any system with n degrees of freedom and n generalized coordinates, so the same amount of degrees of freedom as generalized coordinates, we can have n Lagrange equations that have the same equations of motions. Right? So that's what we said last time. So for any, again, so with any, and this is going to come up a lot today, any system with n degrees of freedom, n generalized coordinates, we have n Lagrange equations with the equations of motions, okay? So we have 4 examples to do today. And now these are going to be the exact examples that you might see when you're doing Lagrange mechanics. We're just going to start and go one by one. The first 2 are relatively straightforward, and then the second 2 have some things we should unpack as we go along with them, right? So they're 4 things that you would see like in a general physics course. You might see some of these examples, but you might not have the ability to like really understand some of the things going on until you understand the Lagrange mechanics behind it. So now what do we do with this, right? Can we do some examples? And we have several examples. The first example is an Atwoods machine. Okay? An Atwoods machine is you have, let's see, we have a frictionless pulley. Oops, let's do like the picture that's in my notes. We have a frictionless pulley with a couple ropes, or with one rope, and a couple of masses is what I meant. M2, M1. It has some radius r, and we're gonna basically label this distance as one of the generalized coordinates. And we're going to take this distance and we're going to see if we can write this in terms of 1 generalized coordinates with 1 degree of freedom. Okay? Okay, let's just keep going. All right. All of these are going to be frictionless. Example. We don't really deal with, when we're talking about action, we don't really deal with friction, do we? Anyways. So let's talk about this machine. I think the setup is right. Yeah, we got mass 1, mass 2, x, y, and r. We can talk about the total length of the string. Total length of the string is going to be written as the following: x plus y plus pi r is equal to L. The length of the string. So if we wanted to rewrite one of our two variables in terms of the other, so we're gonna rewrite y in terms of x plus some constant, right? Where all of the rest of this is just some constant, right? So pi r and l is just some constant. We don't really care too much about them. And well, we'll get to the part where we don't care about it. But x is our generalized coordinate, right? So x is our generalized coordinate. And we can start to worry about the kinetic energy of the system. The kinetic energy of the system, T is equal to 1/2 m1 x dot squared plus 1/2 my dot squared. But now again, we don't really want to write when we get to the Lagrangian phase, eventually we want everything to be in one coordinate, so we're going to have to rewrite all of the y's in terms of x's. So this actually turns into 1/2 m1 plus m2 times x dot squared. Okay, so there we go. Now we have the kinetic energy in terms of just x. So then what can we do with the potential energy? Potential energy is roughly the same. Well, it's roughly going to be a similar process. X minus m2 gy, and then we're going to set that equal to, and we're just going to turn x or y into x. And what do we get? We get minus m1 minus m2 quantity minus the quantity m1 minus m2 and gx plus some constant. Okay? Now this is the part where we write the whole Lagrangian. And the whole Lagrangian is written as t minus u. So we can write everything out. 1/2 times mass 1 plus mass 2 times x dot squared plus m1 minus m2 times gx. And we're not going to worry about the constant because at the next level, which we're going to be taking the equations of motion, we're going to be taking the equations of motion and we're going to take the derivative of the Lagrangian with respect to the generalized coordinate, and the constant's going to go away. So let's do that. The equations of motion are given by the partial of the Lagrangian with respect to x, which is our generalized coordinates, d dt, partial of the Lagrangian with respect to x dot. Now this is the equation, this is our Lagrange equation, right, for the equations of motion. So what we have to evaluate this, and we're going to evaluate this at every turn. Every time we get to this step, we're going to have to put in the spots. So on the left-hand side, we'll get m1 minus m2 times g, which is equal to m1 plus m2 times x double dot. Okay? And then we can solve for x double dot. X double dot is going to be equal to m1 minus m2 divided by m1 plus m2, and that quantity multiplied by g. So now we can find, and I guess the whole point of this goal was to find the Lagrangian. So we can find the Lagrangian and talk about, you know, the Lagrangian, and likewise we could also find the action using what we know, what we learned about from earlier in this series. And then the second part is we can find the equations of motion, and then lastly the acceleration. Now, we can think about this kind of in Newton's terms, right? If we were to do free body diagrams for this, we would have, you know, the mass on the left-hand side would have some force due to gravity, and then some tension. Let's call it T. And then the other side, you know, would have another, let's say, force force of gravity of 1. And we have some tension again here, and the force of gravity, we should be the same as the picture, right? So force of gravity of the mass 2 and the force of gravity of mass 1. And now we're letting it move. Like, we don't want to say that it's not having any motion, so we want to make sure that it's accounting for some type of acceleration. So we could set up our equations of motion, or our equations. I think I have room right here. Let me try to do it right here. And we have m1g minus t is equal to m1 x double dot, which is the acceleration, so just mass times the acceleration. Is that on the screen? Yeah, nice. And then m2, or t minus m2 times g is equal to m2 x double dot. And then if we subtract the two equations, we'll get, or add the two equations, excuse me, then the period will go away, or the period, the tension will go away, and we'll get this nice x double dot is equal to m1 minus m2 divided by m1 plus m2, quantity all multiplied by g. Okay? Quantity multiplied, oh, come on. Quantity multiplied by g. There we go. So, like, we could do this with Newton's motions, we have Newton's things as well, but we have to consider the tension, which is a constraining force. And one thing that's really nice about the Lagrange mechanics is we don't really need the constraining forces. So I don't even know what it would mean to have friction if we don't actually need the normal force in Lagrange mechanics. But again, this is something I just haven't really thought about or worked on myself. But again, it is about the action, so. Okay, so this is the Atwoods machine. Oh, I just dropped my chalk. You were too young. Sorry, friend. We're gonna retire you for a little bit and let you rest.